So here's the question that I ended the previous part of the lecture with. And the only thing the box is touching is the conveyor belt. And so the conveyor belt will exert a perpendicular force on it and possibly a friction. Well, the box isn't slipping, and so the type of friction must be static. And to get this acceleration up the slope, that static friction has to point up the slope. And so this one is correct. Let's think about this situation of a cart on a table attached to a string which goes over a pulley to a hanging mass. And we'll draw the free body diagrams for both and just think about them a little bit. So what we know ought to happen when we release this whole arrangement is that the cart is going to accelerate to the left because the string is pulling it that way, and the mass ought to accelerate down. So I'm going to start with the free body diagram of the cart, and so I've listed the agents and the forces that they'll exert. The table is just going to push up. And then there will be a gravitational force down, and the string is going to pull to the left. And we already know that the cart accelerates left. Notice that I've made the string horizontal. If I hadn't, this force wouldn't be horizontal, but we certainly expect the vector sum of forces on the cart to be horizontal. And so if this force wasn't horizontal, we could have a rather complicated situation where we still have to get a sum of forces that's horizontal, but that would tell us that the vector sum of forces would be equal to only the horizontal part of the force exerted by the string. So that's why I've put the string horizontal. It's a much simpler situation than this. Now I'll do the mass, and once again I've indicated the agents, and in particular the only contact force is the one due to the string, because that's the only thing the mass is touching. And so it's a very simple free body diagram. And I've deliberately made the gravitational force bigger than the force that the string is exerting because we know that the acceleration of the mass should be down, and so the vector sum of forces should be down. Now the only other thing to note is that because these forces that the string is exerting on the cart and mass are probably quite a bit bigger than the gravitational force on the string, that means that these two forces that the string exerts, one on the cart and one on the hanging mass, should be about equal in magnitude. Any object moving through a fluid experiences a drag force, and in everyday language fluid means a liquid, but to a physicist fluid means anything that flows, so generally a liquid or a gas, and drag is often referred to as air resistance. Drag opposes the relative motion of the object and the fluid. I'll explain that more in a moment. But at low relative speeds, we can generally ignore drag forces because they're small. Let's think about a falling Nerf ball and the direction of the drag force on it. It is falling down, and so relative to the air, which is presumably stationary, it's moving down. And so unsurprisingly, the drag force, which is that contact force due to the air on the ball, is pointing up. But now let's think about a windmill to get a better idea of the relative velocity dependence of this direction. So the windmill itself is not moving, at least relative to the ground, but the air is moving in this picture, presumably to our left, which means you could say that the windmill, relative to the air, is moving to the right, and the drag has to oppose that. And so the drag force will be to the left, which tells you that the force that the ground is exerting on the windmill needs to have a significant horizontal component, otherwise the windmill blows away or blows over.